In this video, we have solution stoichiometry about ions, and we're just going to look at this qualitatively. So I'm going to take this problem right here, and we're going to solve that quantitatively later. But right now, we just want to really write our equation, our balanced molecular equation, a total ionic equation, net ionic equation, and then take a look at a microscopic level of what that looks like at the molecular or ionic level. So we have copper nitrate, let's not worry about the amounts, and sodium hydroxide. They're both solutions. So it's copper 2 nitrate, copper's +2, nitrate's -1, so I balance it CuNO3 2. Sodium hydroxide +1, -1, I balance that. We're going to do a double displacement, a partner switch. Copper goes with the hydroxide, giving me CuOH2 because copper is +2 and OH is -1. Then Na is +1, NO3 is -1. So I write the balanced chemical formula first. Then I have to go back and put the correct coefficients in front to write the correct balanced equation, which I do here. That is my molecular equation. I could put aqueous here, aqueous here. You look at a solubility table or do an experiment, you'd find out copper hydroxide is a solid. And I didn't say anything here, but this should be aqueous as well. All right, let's go to the next thing, and that is breaking up what really happens when these things get put in water. And to write the total ionic, I think I'm going to scroll down and almost look at this picture. So I have a container with copper nitrate in here, and there's just not one molecule. There's millions and millions. But what happens is copper nitrate is really strongly attracted to each other. It's an ionic bond. Yet water has a positive and a negative end. And what happens is the negative part of water attracts to the positive part of copper. And the positive part of water attracts to the negative part of nitrate, and it pulls it apart. Remember, for every copper nitrate, there's tens to maybe even hundreds of water molecules pulling. So this ionic compound can be pulled apart when it's put in water. So that's your copper nitrate, which ends up being a pretty dark blue solution. Let's see, sodium hydroxide, the same thing. It's dissolved in water and actually very soluble, and it breaks up into Na pluses and OH minuses. What do you get more of, NH plus, or I'm sorry, Na plus or OH minus? You get the same amount of each because you want to balance the charge at 0. This is a clear solution. Okay, that's referenced up here when I just take the copper and break it into copper +2, and for every 1 copper +2, I have 2 NO3 minus. The NaOH, I put 2 Na plus and 2 OH minus because I keep that coefficient right out there. Notice this subscript becomes a coefficient because it's no longer attached. So this subscript becomes a coefficient because it's no longer attached. It shows it's separate. It's not an NO3 attached to each other, but it's an NO3, two separate entities. Okay, I get to CuOH2, so it is a copper with 2 hydroxides attached. That is a precipitate. It'll be kind of a light blue precipitate. I think we did a lab with that last year in the Bretts. We got those and put them in test tubes, and we get this precipitate, which would sink to the bottom over time, and it would happen much more quickly if you spun it around in a centrifuge. The last one is the NaNO3, and those things are just ions floating around at the end. So looking at this, you can say, oh, these are just ions floating around. These are just ions floating around. You combine them. Now, if there's no reaction, you just get a bunch of ions floating around. Nothing would form a precipitate. But what happens, even with this amount of water, the copper and the hydroxide so attracted to each other, the water can't split it up, so it does sink to the bottom as a precipitate. The Na pluses and the NO3 minuses are floating around at the beginning, at the end. They're not really part of the reaction. They're called the spectator ions. Okay, the precipitate would be down here. If we go to a total ionic equation, we'd say what's really happening, I mean, what's making the reaction? It is the stuff with the copper and the hydroxide. 1 Cu +2 plus 2 OH minus forms CuOH2. AP folks will typically ask you to write like net ionic equations. So you break this all down. Do you have to put the coefficients? Typically not, okay, unless specifically asked for. If I see this +2 or -1, I know it's an aqueous substance that we're dealing with, and I'll know that this is a solid right here. Okay, I believe that's, oh, just one other thing to add to this If there's an excess reactant, then you'll probably see that in here. Like if NaOH was in excess, you'd probably have some OHs floating around here. Or if copper was in excess here, you'd have some of those here. I didn't show that in this diagram to keep it simple, assuming you had no excess or limiting reactant. All right, thank you.